What is polarized light? This is, and so is this. All of this is polarized light. Here, let me help you with that. When I bought this circular polarizer for my camera, it made me wonder, what is polarized light and how the heck can it be circular? First, let me show you what it does. The most important thing it does is remove reflections. It also generally increases the saturation, meaning things look a little bit more colorful, sky looks darker and more blue, and leaves look more green. See, if I twist the polarizer, I can remove the reflections from this river. It does that by polarizing the light entering it, which causes some already polarized light to be reflected instead of passing through the filter and becoming part of your photo. So how does this work? Well, to get circularly polarized light, you first need polarized light. And to get polarized light, first you need light. And to get light, first you need to invent the universe. So, as far as we know, the universe is made up of space and time and some fields. And that's pretty much it. A field is just a way in which we assign a value to every point in space and time. A field is kind of like the surface of the ocean. Every point on the ocean's surface has a particular height at a given time. And just like the ocean, fields have waves which move through space and time. One of these fields is the electromagnetic field. Every point in space and time has an electromagnetic value. But that value isn't just a number, like the height of the water in the ocean. It's actually a vector, which is like an arrow. It has a particular direction and it has a magnitude. Light is an electromagnetic wave, and it's a transverse wave, meaning that it oscillates in a direction that is perpendicular to its direction of travel. So if light is traveling out of this laser pointer this way, that means that the electric field is maybe oscillating up and down or side to side. Now, you might be thinking, what kind of universe is this? Where are all the particles? Where are the protons and the electrons and the tacos that I'm used to seeing in the real world? And isn't light actually made of photons? The answer that you might have heard before is that light sometimes behaves like a wave, but sometimes like a particle. And even electrons do some wave-like things sometimes, like if you put electrons through two slits, you'll get this neat interference pattern. But when you stop and look at them, yeah, they're particles. The detectors only detect one photon's worth of energy at a time. Well then, how did the electrons make the interference pattern? If they were particles, it would just be two big splotches. I don't know. Some kind of particle wave duality, mumble. You realize you're not mumbling, right? You're just saying the word mumble. But the truth is, physics has already produced a much better answer, and it's like 40 years old. It's called quantum field theory. Okay, don't freak out. I'm not a physicist. I'm not actually going to try to explain quantum field theory because, frankly, I don't actually understand how it works. But all you really need to know is that the universe is just made out of waves. Nothing but waves. Everything is waves. Doesn't that feel better? Sometimes those waves get into a little excited, stable state that we call a particle. But in quantum field theory, it's called field quanta. Really creative name, right? But that's all there is. There's just waves. Well, there's also tacos, but I'm pretty sure that those are just wavy field quanta that are in a crunchy, warm tortilla. Field quanta. So who cares? What's so different about waves and particles? Why does it matter? So it has to do with that old interference pattern. See, there's this thing called vector addition, and because those vectors can have negative values, that means that they can cancel each other out. You can have a positive value and a negative value, and then you end up with nothing. Okay, let's look at this diagram for a little bit. A wave has a phase, a wavelength, and a polarity. The phase is just the position of the crests and troughs along the wave. The wavelength is the distance between any two of them, and the polarity is the direction of our wave vector at any given point. A laser beam looks kind of like this picture because it generally has one phase, one wavelength, but normal everyday light is really complicated. It has a whole bunch of polarities and wavelengths and phases all at the same time. Light is way more awesome than this diagram. Visible light is just electromagnetic radiation within the visible range between 400 nanometers and 700, and the wavelength of light determines its color. Okay, so now we have the universe and we have light. How does it become polarized? Well, the most common way is for it to be reflected or refracted. When light hits a surface, the angle at which it hits it is called the angle of incidence, and the reflection comes back up with the opposite angle. And the refraction goes down through the surface and gets bent. How much it gets bent is determined by the refractive index of the substance that it's going into, and also the one that's coming from. This is described by Snell's law. Air has a refractive index just a little bit over 1. Water has a refractive index just a little bit over 1 1/3, and glass has a refractive index around 1 1/2. Depends on the type of glass. Usually, denser materials have a higher refractive index. Okay, so it turns out reflections and refractions get polarized. When light hits a surface at just the right angle, called Brewster's angle, the reflection is totally polarized. The wave along the same plane as the incident light and the surface gets totally canceled out, and what you're left with is only light that's oscillating side to side. The light that gets refracted through the surface is also slightly polarized in the opposite direction. So what is Brewster's angle? Well, we can find it using Brewster's law. It's the arctangent of the second refractive index over the first refractive index. Does this ratio look familiar? Yep, it's the same one from Snell's law. Metallic reflections don't do this. That's because conductive materials don't refract electromagnetic waves, they just reflect them. The other more expensive way to get polarized light is with a polarizing filter. But it's not really a filter, so we probably shouldn't call it that. Filters just filter things out, whereas this is actually bending the light. You might be tempted to think that light coming into the filter has a bunch of different photons that have different polarizations, and it's just blocking the ones that don't have the same polarization as the filter. But that's actually not what's happening. Sure, it absorbs and reflects some of the light, but not all of it. So check this out. If I take two polarizers and I turn one 90 degrees so that they block out most of the light, and then I add a third one at a 45-degree angle, it actually lets more light through than just with the two polarizing filters. So how does the linear polarizer work? Well, it actually has a lot of long conductive molecules in it that are arranged like a comb all in the same direction. When light hits the polarizer, it can't penetrate if it has a polarization in the same direction as the conductive molecules because they reflect the light. It becomes just like a metallic reflection. In order to work, the gap between the conductive molecules needs to be about the same size or a little bit smaller than the wavelength of the light that we're trying to filter. This same principle works with microwaves. Microwaves sound small, but they're actually about 1 centimeter, which is why they don't fit through this mesh. If the conductive lines go in one direction, it's a polarizer. If wires go in multiple directions like this, then it's called a Faraday cage. Radio waves are even bigger than microwaves, which is why if you stick your cell phone into the microwave and close the door, you won't get any bars because all of the radio waves are being filtered out. If you try this, make sure you don't turn the microwave on because your cell phone will not like it. So, how do you make your newfangled polarized light into circular polarized light? Easy. Just put a material after your polarizer which has a different refractive index in one direction than it has in the other. The easiest way to make something like that is to stretch that material in one direction. Then you take that material and you put it at a 45-degree angle relative to your polarizer. That makes the light slow down in one axis more than the other, which causes the light to develop a circular wobble. You can see this start to work if I take two polarizers that are opposed to one another and then I stick the material in between. So if I do this without really stretching it, it doesn't really look any different. Then if I take the material at a 45-degree angle and start to really stretch it, then you can see where there's stress on the material, then the polarizers are no longer working together to filter out the light, because the light which is coming in is getting linearly polarized, and then circularly polarized, and then linearly polarized again. But circularly polarized light goes pretty easily through the linear filter. Here's another way that you can see polarization. Vibrating strings also have polarity. If you look down the length of one, I could pull the string up and give it a up and down polarization, or I could pull it from the side and give it a side to side polarization. And if I'm really careful about slowing the string down at a 45-degree angle, I could even create a circular polarization. We can also see why this works with good old vector addition. If we take a polarized wave, we can always think of it as two other waves which are 90 degrees from one another. One of them experiences one refractive index, and the other experiences a higher refractive index which slows it down. If we slow the second wave down so that it's 90 degrees out of phase with the other wave, then we can see that this wobble pattern emerges where we have the wave cresting at the top, and then at the right, and then at the bottom, and then at the left, and so on and so forth in this circular pattern. And if we add the waves together, we get a circular wave. Well, why would you want this? When we have our circularly polarized light, it behaves like unpolarized light, which is why it's able to pass through a second linear filter, and it's able to go into the sensors in your camera and behave like natural light. If the sensors are biased towards one polarization or the other, it won't matter and it will still work properly, whereas if you just take your linear polarizer and apply it to your camera may have a hard time figuring out how much light is actually in the scene. Seems okay, it's not really a big deal. I don't know. Sorry they're not very high quality, they're a little scratchy. One more thing that I want to show you. First, I'm going to put the circular polarizer back onto the camera, but it's just going to act as a polarizer. Okay, one polarizer is on the camera. Now I'm going to take this linear polarizer and add it to the camera. This way it doesn't do anything. This way it gets a lot darker. It also gets very blue, depending on how I orient it. So I'm going to orient it just so that we lose some of the blueness, and it just looks kind of foggy. Now I'm going to hold up another linear polarizer, and it will look dark blue. If I turn it this way, it turns purple. If I turn it this way, it turns green. And even more, it turns yellow, kind of orange, kind of red, pretty clear, and then it goes back to purple again. I've got a whole rainbow of color just by orienting this linear polarizer differently. And I got more. I have lots of them. I get different colors. So what's going on here? You tell me. So this doesn't work. It doesn't look any different to me, but it looks different to you. So I got some idea what's going on there, but I'm not really sure. Let me know in the comments what you think is really happening. If you want me to make more videos like this, click the like button. And if you want to see them, click the subscribe button. If you can't replicate it, it's not science, so I put links in the description for some of the products that I purchased in order to do these experiments. Thanks for watching.